The Semantic Field Registry maintains a centralized repository of type information for all declared fields within a compilation unit. Each field entry contains the declared type, inferred type constraints, nullability assertions, and references to the site of declaration. The registry is constructed during the parsing phase and remains immutable after initialization. Access to registry entries is mediated through a read-optimized hash table keyed by fully qualified field identifiers. Type annotation resolution proceeds in two distinct phases. The primary phase occurs during initial field declaration, where the annotation token stream is parsed and normalized into an internal representation. The secondary phase occurs lazily upon first access, where independent type information is resolved and cached. This two-phase approach minimizes unnecessary computation, while ensuring all type constraints are eventually resolved. The annotation parser recognizes 12 distinct primitive type tokens: integer, floating point, boolean, character, string, byte array, void, null, undefined, variant, timestamp, and enumeration. Complex types are constructed recursively from primitives through composition operators, array notation, optional notation, union notation, and generic parameter binding. The parser maintains a stack of unresolved type references, resolving them in post-order traversal once all constituent types are available. Nullability inference operates on a three-state model: explicitly non-null, explicitly nullable, and inferred null. Fields declared with non-null modifiers are recorded as definitively non-null. Fields declared with optional or nullable modifiers are recorded as explicitly nullable. Fields without explicit modifiers undergo inference based on assignment patterns observed in the compilation unit, defaulting to inferred null status when ambiguous. Generic type parameters are stored in a separate parameter table linked to each field entry. The parameter table maintains an ordered sequence of type variable bindings, each recording the parameter name, variance annotation, and upper and lower type bounds. When a generic field is referenced, the parameter table is queried to determine the concrete types with which the generic has been instantiated, and type substitution is performed recursively. The constraint solver validates type assignments against declared field constraints. When a value is assigned to a field, the constraint solver obtains the field's type specification from the registry and verifies that the value's inferred type satisfies all declared constraints. The solver implements a unified type compatibility algorithm that handles subtyping, variance, and coercion rules. Failed constraints are recorded with source location information. The field registry maintains a visibility matrix that tracks which fields are accessible from each scope context. Visibility is determined by declared access modifiers. Public fields are accessible everywhere. Protected fields are accessible within the containing class and subclasses. Private fields are accessible only within the containing class, and internal fields are accessible within the containing package. The visibility matrix is computed during initialization and consulted at each field reference site. Alias resolution handles situations where a field name refers to a previous declaration that has been renamed or reassigned. The registry maintains an alias chain for each field entry, recording all historical names and the declarations to which they refer. When a field reference is encountered, the alias chain is traversed to locate the canonical declaration. Cyclic aliases are detected and reported as errors during initialization. Field initialization state is tracked through a three-state machine: uninitialized, tentatively initialized, and definitively initialized. Fields enter the uninitialized state upon declaration. Assignment statements transition fields to tentatively initialized if the assignment is unconditional, or remain uninitialized if the assignment is guarded by a condition. Definitive initialization requires that all execution paths leading to a field's use have assigned a value to that field. The registry supports field shadowing, wherein a field declaration in a nested scope obscures a field declaration in an enclosing scope. The resolution algorithm prioritizes declarations from innermost to outermost scope. When a shadowing situation is detected, both the shadowed and shadowing declarations are recorded in the field entry's metadata. Access to shadowed fields is permitted only through explicit scope qualification or through an upward scope reference operator. Type refinement occurs when control flow analysis narrows a field's inferred type. After a conditional check that verifies a field's type, the field's type is refined within the guarded branch to the more specific type indicated by the check. Refinement information is stored in a separate refinement table keyed by statement identifier and field reference. The refinement is discarded when control flow exits the guarded scope. Default value specifications are optional annotations on field declarations that provide values to assign when a field is constructed without an explicit initialization. Default values are stored in the field entry and are consulted during object construction. If a default value specification references another field, that reference is recorded as a dependency and is resolved only when the default value is actually used. Variance annotations on generic fields control whether subtype relationships on type parameters are preserved in the field's type. Covariant fields preserve subtype relationships. If type A is a subtype of type B, then field A is a subtype of field B. Contravariant fields reverse subtype relationships. Invariant fields permit no subtype relationship unless the type parameters are identical. Variance is validated during field declaration and enforced during type checking. The registry exports a query interface that permits external tools to inspect field information. Queries may retrieve all fields matching a predicate, all fields visible from a given scope, or the complete type information for a specific field. Query results are computed on demand and are not cached, ensuring that results reflect the current state of the registry. Queries that scan large portions of the registry may be throttled to prevent resource exhaustion. Error recovery in the annotation parser employs a synchronization-based strategy wherein parsing resumes at the next valid annotation boundary when a parse error is encountered. This permits multiple errors to be reported in a single compilation pass. Error information, including source location and predicted recovery point, is associated with the affected field entry. Subsequent analysis phases skip fields marked with parse errors to prevent cascading failures. The field registry is serialized to a binary format for storage in compiled artifacts. The serialization process writes field entries in declaration order, compressing type information and resolving all internal references to offsets. Upon deserialization, the registry reconstructs the internal data structures and validates structural consistency. Deserialization is performed incrementally so that fields are available for use as they are reconstructed, rather than requiring the entire registry to load before use begins.